There's a river in the Atlantic that carries more water than every river on land combined. You cannot see it from ashore, but if it ever stopped flowing, hundreds of millions of lives would change within a decade. London sits farther north than most of Canada's big cities. A big part of the reason it isn't buried under snow half the year is a current of warm water most people have never thought about. This is the story of that current, of what it does for us quietly every hour of every day, and what the world might look like if it ever faltered. It is a story with real science underneath it, and a popular headline sitting on top that turns out to be almost entirely wrong. We'll get to both. But first, let us understand what is actually at stake. Because the people who depend on this warm water are not a distant abstraction. They are most of Europe. Imagine two cities at the same latitude. One is mild and green through winter. The other spends months locked under ice. The difference between them is largely the ocean. The warmth carried north across the Atlantic keeps Western Europe several degrees milder than it has any right to be, given how far from the equator it sits. Paris, Berlin, Dublin, Oslo. All of them enjoy a climate softened by heat that was gathered thousands of miles away in the tropics and delivered by moving water. Without that delivery, the same cities would face longer, harder winters. The growing season would shrink. The rhythm of European life, built over centuries, would begin to shift. But Europe is only the most famous customer. The reach of this system extends far beyond the North Atlantic, into places you might never connect to it. Across West Africa, the seasonal rains that feed hundreds of millions of people are tied to the position of a great belt of tropical weather. That belt is sensitive to the temperature of the Atlantic. Shift the ocean's heat, and you can shift where the rain falls. The monsoon that farmers count on can arrive late, arrive weak, or wander off its usual path. Out in the open ocean, the same currents shape one of the richest fisheries on Earth. Cold, nutrient-heavy water and warm surface flows meet, and life explodes at the boundary. The cod, the herring, the vast schools that have fed North Atlantic nations for 1,000 years, all live inside a delicate temperature structure the currents maintain. And there is one more group with a quiet stake in all this, one that rarely appears in the story. The cities of the United States Atlantic coast. The same moving water helps hold the sea surface at a certain tilt along that shoreline. Weaken the flow, and the ocean can pile up higher against the coast. Consider how invisible this dependence is. Nobody in Madrid or Copenhagen wakes up thinking about the chemistry of the ocean near Greenland. Yet the mildness of their morning, the price of their bread, and the reliability of their seasons all quietly trace back to it. Before we even understand how this machine works, we can already name who is riding on it. Europe's mild winters, Africa's rains, the Atlantic's fish, America's coastline. That is an enormous amount of the modern world balanced on a single flow of water. Which raises the obvious question: what exactly is this thing? Start at the surface in the warm shallows near the equator. Sunlight pours in for months, and the sea there soaks up heat like a vast dark blanket. The winds and the spin of the planet gather that warm water and drive it westward, then bend it north, hugging the eastern edge of North America. This is the Gulf Stream proper. A ribbon of warm water, deep blue and fast, sliding up past Florida and the Carolinas like a moving wall in the sea. It is genuinely enormous. Oceanographers had to invent a unit of their own just to measure flows like this, and the heat it carries north is on a scale difficult for the human mind to hold. As it travels north and east across the Atlantic, it does what any warm thing does in cold air. It gives its heat away, breath by breath, into the winds bound for Europe. Those winds, warmed by the water, roll ashore over Ireland, Britain, France, and Scandinavia. That is the free heating system Europe has enjoyed for the whole of its recorded history. But the story does not end when the water arrives. Something happens up near Greenland and the Nordic seas that turns this into a loop, a genuine circulation. By the time the water reaches those far northern seas, it has lost much of its heat. It is now cold. And crucially, because so much has evaporated along the way, it is also very salty. Cold water is dense. Salty water is dense. Cold and salty together is the densest surface water in the ocean, and dense water does one thing. It sinks. In a few special regions of the North Atlantic, the surface water grows so heavy that it plunges downward in vast, slow columns, sinking thousands of feet into the deep. This sinking is the engine. It is the part almost nobody pictures, and it is the part that truly matters. The pulling down of cold water is what keeps the whole loop turning. Once at depth, that water spreads south again in a slow, cold river along the ocean floor, creeping back toward the equator over years and decades. Warm water north near the surface. Cold water south along the bottom. A single connected overturning loop wrapped around the Atlantic like a belt turning on its side. It is worth pausing on the scale of time folded into this loop. A single parcel of water can take something like 1,000 years to complete the full journey, sinking in the north, creeping along the deep sea floor, and finally rising again on the far side of the world. And heat is not the only cargo. This same circulation drags dissolved carbon dioxide down into the cold deep and lifts nutrients back toward the sunlit surface. It is not merely a heater for Europe. It is part of how the whole planet breathes. Scientists call this larger system the Atlantic Meridional Overturning Circulation. It is a mouthful, so most people shorten it to the AMOC. Remember that name. The whole real story turns on it. You may also have heard it described as part of the Great Ocean Conveyor, a planet-spanning belt of moving water that redistributes heat, carbon, and nutrients around the entire globe. The sinking near Greenland is one of the master switches of that conveyor. Slow the sinking, and you slow the pull. Slow the pull, and the warm surface flow northward begins to weaken. And here is the unsettling part. That sinking depends on the water staying salty and heavy. Anything that makes the northern ocean fresher and lighter could jam the engine. Fresh water is exactly what a warming world delivers. Melting ice, heavier rainfall, and rivers swollen with runoff all pour lighter water onto the very spot where the ocean needs to sink. If enough fresh water floats on the surface up there, it can act like a lid. The dense sinking slows, and a slower engine means a weaker current reaching Europe. This is not a wild theory dreamed up for a documentary. We know this loop can weaken because the Earth has run the experiment before and it left records we can read. To find the clearest example, we have to travel back nearly 13,000 years to the end of the last great ice age, when the world was already climbing out of the cold. The planet had been warming for centuries. Ice sheets were retreating. Forests were creeping north. Everything pointed toward the mild world we live in today. And then, abruptly, it reversed. Within a span that may have been as short as a few decades, the North Atlantic region plunged back toward near glacial conditions. This event has a name: the Younger Dryas. Winters returned with a vengeance. The warmth that had been spreading across Europe drained away. In places, the climate lurched backward by thousands of years, almost overnight in geological terms. And it held that way not for a season, but for well over 1,000 years before flipping back to warmth just as suddenly as it had cooled. Picture the people living through it. Communities across the northern hemisphere watched the climate they had adapted to unravel within a single generation. Landscapes that had turned green with the warming reverted, once again, to cold and open tundra. How do we know all this so precisely? Because nature keeps its own archives, and scientists have learned to read them layer by layer. Deep in the Greenland ice sheet, snow that fell each year was buried and compressed into ice, trapping tiny bubbles of ancient air and chemical clues about the temperature of the day it fell. Drill down through that ice, and you drill down through time. Each layer is a page. And the pages from the Younger Dryas record a shockingly fast, brutal cooling. On the sea floor, sediments tell a matching story. The shells of tiny creatures, the grains dropped by melting icebergs, all preserve a record of when the ocean's circulation faltered. The leading explanation ties it directly to the loop we just described. A colossal pulse of fresh meltwater flooded into the North Atlantic, capping the ocean and choking off the sinking. The overturning slowed dramatically. The northward heat delivery weakened. And Europe, sitting at the end of the pipeline, felt the cold rush back in within a human lifetime. That is the crucial lesson from the deep past. This system does not always change slowly and gently. Under the right push, it can shift fast and stay shifted for a long time. The Younger Dryas is the sharpest case, but it is not the only one. The paleoclimate record holds several episodes where the Atlantic overturning appears to have stumbled and reorganized. Each one leaves the same fingerprint. A cooling clustered around the North Atlantic, shifts in tropical rainfall far away, and a world that took centuries to fully settle again. So the machine is real, its off switch is real, and history proves it has been thrown before. The natural next question is uncomfortable. Is anything nudging that switch today? This is where we move from ancient ice into the present, into measurements taken by instruments floating in the water right now, and satellites watching from above. The concern begins with Greenland. Its ice sheet is losing mass, shedding hundreds of billions of tons of fresh water into the sea in a warming climate. That fresh water flows into exactly the region where the ocean is supposed to grow salty and heavy and sink. It is the same ingredient that helped trigger the ancient cooling. And when researchers map the surface temperature of the world's oceans, almost everything has been warming. But there is one strange patch that has not. A stubborn cold spot south of Greenland. Scientists have nicknamed it the cold blob. On maps of a warming ocean, it sits as a lonely island of blue in a spreading sea of red, and one plausible explanation is a weakening of the northward heat delivery. Piecing together direct measurements, satellite data, and clues locked in ocean records, several studies now suggest the overturning may be in its weakest state in around 1,000 years. Let that land for a moment. Not the weakest in a decade or a century, but potentially the weakest in roughly a millennium. A slow, quiet loss of strength in a system we barely notice. But here candor demands a pause, because this is where the science becomes genuinely uncertain and where careful researchers disagree with one another in good faith. Measuring the strength of an entire ocean circulation is fiendishly hard. Continuous, direct monitoring only spans a couple of decades. Before that, we lean on indirect clues, and clues can be argued over. Here the community splits. Almost everyone agrees the system is likely weakening this century. The fierce debate is over how much, how fast, and whether a true tipping point is near. The major international climate assessments take a cautious line. They judge a complete collapse before the year 2100 to be unlikely, though they cannot rule it out. But some recent studies push harder, arguing the risk is being underestimated and that a critical threshold could be closer than the cautious consensus allows. That disagreement is real, and it is not yet resolved. It helps to think in probabilities rather than certainties. No serious scientist claims to know the exact year of any threshold. The truthful version is a spread of possible outcomes, most of them gradual, a few of them abrupt, and a small tail that is genuinely severe. This is the honest shape of the science. A system almost certainly weakening. A past that proves it can lurch. And a live argument about just how much danger sits in the tail of the odds. So let us ask the question directly. Suppose the worst credible case unfolds. Suppose the Atlantic overturning does not just weaken, but collapses. What would the following years actually look like? We will walk through it as a plausible chain of consequences, decade by decade. Keep one thing in mind throughout. This is informed speculation, built on real physics, not a forecast written in stone. The first thing people would notice is not a wall of ice, but a change in the feel of the winters, especially around the North Atlantic rim. Northwestern Europe would begin to cool. Not overnight, and not everywhere equally, but the mild, forgiving winters would start to harden towards something colder and longer. One way scientists describe it is a shift toward the climate of similar latitudes on the far side of the Atlantic. Think of the harder winters of Newfoundland creeping toward the shores of Europe. Britain and Ireland, so used to gray but gentle winters, could face sharper frosts and more snow. Scandinavia, already cold, could tip toward something more severe still. The change would not be measured only in comfort. It would be measured in energy bills, in burst pipes, in strained power grids, in the simple daily cost of staying warm. Now widen the lens from comfort to food, because this is where a colder, shorter growing season truly bites. Europe is one of the great breadbaskets of the world. A shorter growing season means fewer days for crops to ripen. Later last frosts and earlier first frosts squeeze the calendar farmers depend on. Yields of staple grains could fall. Fields that reliably produced wheat and barley might become marginal. The map of European agriculture, refined over generations, would have to be redrawn under a colder sky. And food does not stay local. A serious hit to European harvests would ripple through global grain markets, nudging prices upward far beyond the continent's own borders. Here is the twist that surprises people. A collapse of this system would not cool the whole planet. The Earth would keep warming overall. The effect is a violent reshuffling of where heat and rain end up. And some of the largest impacts would fall not on the cold north, but on the warm tropics through the movement of the Great Rain Belts. That belt of tropical rainfall we mentioned earlier sits where it does partly because of how heat is balanced between the hemispheres. Cool the North Atlantic sharply, and the belt tends to shift southward. For the monsoon regions of West Africa and parts of Asia, a shifted rain belt is not an inconvenience. It is the difference between a harvest and a failed one for hundreds of millions of people. Rains might weaken or arrive at the wrong time across the Sahel and beyond. Meanwhile, other regions could be flooded by rainfall that has wandered from its usual home. The cruel arithmetic is that the places most exposed to shifting monsoons are often those with the least buffer against a bad year. A wandering rain belt can become a humanitarian crisis. Now cross back to the Western Atlantic to a consequence that has nothing to do with cold and everything to do with the level of the sea itself. When the overturning is strong, it subtly lowers the sea surface along parts of the North American East Coast. Weaken the flow, and that suppressed water is free to rise. On top of the global sea level rise already underway, a weakening circulation could add an extra surge along the shores of cities like New York, Boston, and beyond. That means higher tides, deeper storm surges, and more frequent flooding of streets, subways, and basements that were built for a calmer ocean than the one arriving. For low-lying coastal neighborhoods, a difference of even a few inches changes how often the sea comes indoors. Multiply that across a densely populated coast, and the cost climbs fast. Then there is the ocean's living side, the fisheries that sit inside the currents like tenants inside a house whose walls are quietly moving. Fish do not read maps. They follow temperature and food. Rearrange the currents, and the great fisheries would begin to migrate, collapse in old grounds, and perhaps reappear somewhere new. Fishing communities that have worked the same waters for centuries could find the catch simply gone, move to seas they have no rights to, and no boats positioned for. The base of the ocean food web could shift too. The tiny drifting plankton that feed everything else bloom on a schedule tied to the currents. Disturb the currents, and you disturb the entire pyramid above. Storms would not sit still either. The tracks that steer weather across the Atlantic are guided by the contrast between warm and cold water. Change that contrast, and you change where storms go. Europe could see altered patterns of wind and rain, stormier stretches in some seasons, unexpected dry spells in others, as the atmosphere adjusts to a rearranged ocean beneath it. Now stack all of this together, because in the real world these pressures would not politely arrive one at a time. They would overlap, and they would feed on one another. Each of these strains is serious on its own. Together, overlapping, they would begin to reshape where and how people can live. Regions that became too dry to farm or too flooded to inhabit would push people to move. A herring port with no herring. A wheat town with nothing left to mill. A coastal street that floods on every spring tide. Migration pressure, already one of the defining forces of our age, would intensify. Food prices, sensitive to every bad harvest, would climb and swing. Picture the bread aisle of an ordinary supermarket, where a loaf quietly doubles in price because the wheat behind it failed an ocean away. When food becomes expensive and uncertain, the effects reach far beyond the dinner table into politics and stability. None of this would arrive as a single dramatic day. It would come as a grinding decade, a slow tightening, a world quietly rearranging itself around a current that lost its strength. There's a grim feedback hidden in this too. A sharply colder North Atlantic could, in some scenarios, encourage more sea ice, which reflects sunlight back to space and reinforces the cooling, a self-feeding loop that can lock a shifted state in place for a very long time. It is worth stressing what this scenario is not. It is not a new ice age for the entire globe, and it is not something that simply switches off again on a human schedule. It is a regional upheaval layered on top of a planet that is still, on average, growing warmer. That is the shape of the worst credible case. It is sobering, and it is grounded in real physics. But now we owe you the honest turn, the part that changes the whole picture. Because there's a problem with the very headline that draws people to this topic. The phrase, the Gulf Stream stops. Taken literally, it is almost certainly impossible. Here is the distinction that matters, and that most dramatic coverage blurs. The Gulf Stream and the overturning circulation are not the same thing, and they are not driven by the same force. The Gulf Stream, in its core, is a wind-driven current. It exists because winds blow across the ocean and because the Earth rotates, piling water against the western edge of the Atlantic. As long as the winds keep blowing and the planet keeps spinning, that western boundary current keeps flowing. You cannot switch it off any more than you can switch off the rotation of the Earth. So the popular image of the Gulf Stream simply halting, of the warm water freezing in place, is physically wrong. The wind-driven river of the Atlantic is not going anywhere. What scientists actually worry about is the other system layered on top of it. The density-driven overturning, the great overturning we met earlier, the part powered by cold, salty water sinking near Greenland. The confusion between the two systems is understandable. On a map, they trace nearly the same path across the Atlantic, warm water heading north. But one is pushed along the surface by the wind, and the other is pulled downward by density in the deep, and only the second of them is truly fragile. That overturning circulation is the vulnerable one. It is the part that fresh meltwater can slow. It is the part the ancient record shows has weakened and reorganized before. So the accurate statement is not that the Gulf Stream will stop. It is that the overturning circulation riding along the same path could weaken significantly, dragging much of the northward heat delivery down with it. This is why careful scientists wince at the disaster movie version. The famous film that froze New York solid in a matter of days got the physics cartoonishly, spectacularly wrong. There is no flash freeze. No wall of instant ice chasing people down hallways. The real risk is slower, subtler, spread across years and decades, which in some ways makes it harder to confront. So the verdict is double-edged. The popular headline is technically false. And yet the real story underneath, it is both more subtle and, in its own way, more unsettling. More unsettling because a slow risk is easy to ignore. A current that fades by a few percent a decade does not make headlines every morning. But the direction of travel is what alarms researchers. And here we must hold both truths at once. A full collapse this century is judged unlikely by the cautious consensus, but unlikely is not impossible. And when the downside is this large, even a modest probability deserves serious attention. That is the uncomfortable logic at the center of this field. So what is actually being done? The reassuring answer is that we are no longer flying blind. For the first time in history, we are watching this system in something close to real time. Strung across the Atlantic are arrays of instruments, anchored moorings that measure temperature, salinity, and flow at many depths continuously, day and night, year after year. One long-running observation system stretches right across the ocean at a key latitude, taking the pulse of the overturning circulation and turning a once-invisible flow into a line on a graph. Fleets of drifting robotic floats dive and surface across the world's oceans, radioing back their measurements. Satellites track the height and temperature of the sea surface from orbit. For the first time, if this system begins to falter in earnest, we should be able to see it happening rather than reconstructing it centuries later from mud and ice. A tipping point you can watch approaching is a very different thing from one that arrives as a total surprise. An early warning buys the single resource every hard decision depends on, which is time. And the deeper cause here is not mysterious. It is the same warming that melts the ice and freshens the sea. Every fraction of a degree of warming we avoid is also a fraction of a degree of pressure taken off this ancient loop. The overturning circulation is, in the end, one more reason the climate story is not abstract. A civilization that tracks a deep ocean current from orbit is still, in the end, dependent on that same current continuing to behave the way it always has. The satellites are new. The dependence is older than any of our maps. Time to gather the takeaway, free of both panic and false comfort. The Gulf Stream is not going to stop. That much we can say plainly. But the great overturning circulation that shares its path is weakening, quite possibly to its feeblest state in 1,000 years, and the history of the planet shows this system can shift hard and fast. It is a slow-motion risk, not a movie freeze, the kind that is easy to defer and expensive to ignore, sitting quietly in the tail of the possibilities. The scientists themselves disagree on how close any threshold might be. And that disagreement is not a weakness to hide. It is the honest sound of a hard question being worked on in real time. What is not in doubt is how much rides on the answer. Europe's winters, Africa's rains, the Atlantic's fish, America's coastline, all of them tied to a flow of water we cannot see. The deep past whispers a warning, and the present sends faint signals we are only now learning to read. Between the two lies a question with no comfortable answer, only the slow discipline of paying attention to something most of us will never see. Which brings us back to where we began, to that invisible river in the Atlantic carrying more water than every river on land combined. It has been turning quietly for thousands of years, warming cities that will never know its name, feeding oceans, steering rains, holding back seas. And it asks nothing of us in return. Nothing, perhaps, except that we notice it. That we learn the difference between the headline and the truth, and that we keep watching the water patiently, while there is still time to understand it. There's a river in the Atlantic that no one can see. Whether it keeps its strength may be one of the quietest, most consequential questions of the century now unfolding.